Hey, and welcome back, YouTube gang. We've got here a worked example with stationary waves. And this one reads, in an experiment to demonstrate a stationary wave, two microwave transmitters emitting waves of wavelength 4 centimeters are set facing each other as shown. You can see those two transmitters as shown. Looks like there's some value here, D, and a detector. A detector is moved along a straight line between the transmitters. It detects positions of maximum and minimum signal. I'm going to give you some bonus physics right now, YouTube. I wish I had a sound effect that was like, something right there for bonus physics. We'll work on that. Maximum is going to be an antinode, and a minimum, that's going to be a node. Okay. The detector is a distance d from the left-hand transmitter, as shown. Assume that both transmitters are at antinodes of the stationary wave. Which row gives a value of D for a maximum and for a minimum? All right, so this is an antinode, so it's going to open up like this, and it's going to close down to a node right there. This is an antinode, so it kind of opens up, like the wave opens up right there, maximum sort of displacement, but then there's a node right by it. And then we know that like a stationary wave is just a bunch of loops. So you can draw a bunch of loops like this for yourself, or you can try to waveform it. Nice. All right, and then this one's going to go. See how I'm getting my loops? All right, there you go. Got a loopy little waveform there. And this is what I was mentioning earlier. Like, I like to see my waves, that I'm working with. I got to be able to visualize it. I got to work with something like that. Now, there's probably a whole bunch more waves than I've drawn here, but it's kind of representative of what's going on between those transmitters. Like this wave, this transmitter sent out a wave, this one sent out a wave, and they're interfering right in between. They're superposing, and you're getting places where they've constructively interfered, antinodes, and destructively interfered nodes. They tell us the wavelength of the wave. So let's start right here. We're going down half a wave, going back up. That's a full wave right there. Right? So we can visualize that waveform, say, well, that long is 4 centimeters. Let's break it down quarter cycles. From here to here, 1, 2, 3, 4, right? So 1 centimeter brings us from an antinode to a node. Another centimeter brings us to another antinode. If I want another centimeter over, I'm back to a node. So it's basically like every centimeter, we're alternating antinode, node, antinode, node, antinode, and so on, and the pattern continues. So if I can reason that 0 centimeters away is an antinode, right? Because it tells me at the transmitter, there is an antinode. So then I've got nodes at 1 centimeters, at 3 centimeters, at 5 centimeters, at 7. I've got nodes at 47 centimeters. I'm not going to go all the way there. I don't think I've drawn enough waves to do it, but as soon as you've established that pattern of, oh, there's nodes occurring at the odd sort of multiples of, centimeters, then the antinodes are at 0, not at 1, there's a node there, but at 2, there's an antinode. And then here's an antinode at 4, here's an antinode at 6, there's an antinode at 48. And so we can basically reason that all of the maxima, all of the antinodes are going to occur at even numbers. All the minimum or the nodes are going to occur at the odd numbers. And only one combination of choices agrees where the maximum is even and the minimum is odd, and that is choice C. And this has been another worked example with Dr. Schleich.
Right.